are going to continue our discussions on displacement analysis. So, the overview of today's lecture is as shown on the screen. So, we will discuss the problem of displacement, go through the problem of displacement analysis in brief, look at the problem of forward and inverse kinematics, and then finally, we are going to look at an example of this 3R1P chain of type 1. So, in the previous lectures we have looked at displacement analysis and seen what the problem is about. So, we have seen that mechanisms transform actuator inputs to motion outputs. These inputs are the actuator displacements and the outputs are the output link displacements, which may be position and orientation or maybe just position, and the determination of the displacement input output relation is the problem of displacement analysis. So, here I have shown two examples. This is a surgeon's scissors for laparoscopic operation. So, as you know, when the surgeon tries to move this handle, the scissors or the clamp, they close on. So, the problem here is, given the input, what is the output motion? A similar problem is shown on the right. Here we have the aircraft landing gear mechanism. So, I can ask the question, what should be this actuator throw or displacement, so that this wheel closes. So, it is folded. And the inverse problem would be, given the motion of the wheel, what should be the actuator displacement? In the case of robots, remember that robots are mechanisms with degrees of freedom 2 or more. So, in case of robots, like the examples I have shown here, for example, in this case of the excavator, I can have successive displacements of the bin along a certain path. I would like to possibly move this bin along a certain path. So, successive displacements of the bin generates a path for the bin. So, the bin is the output link, or in this case of this Puma robot, I may have a path on which there are points. At individual points, I would like to know what are these angles, and as I move through these angles successively, the end effector of the robot, it traces this path. So, there are two problems in displacement analysis. The first problem is known as that of forward kinematics. So, given the actuator input, find the output displacement. Say for example, I give you the displacements of this actuator and ask you what is the location of the end point. So, given these actuator inputs, what is the location of the end point? So, this is the forward kinematics problem. In the inverse kinematics problem, which is the second problem, we would like to know the actuator inputs which result in a specified output displacement. For example, I have this standing position of the person. I would like to know what should be this actuator throw, how much should this actuator expand. Similarly, in the case of this excavator, I would like to know how much these actuators should expand in what way, so that this can follow a path. So, I would suppose, given this point of the bin, what should be the displacements on the actuator. So, that is the inverse kinematics problem. So, this is the agreed plan that we are moving with. We are considering constraint mechanisms. Subsequently, we will look at robots with open and closed chains. So, let us look at this constraint mechanism, and today we are going to look at the 3R1P kinematic chain. So, this problem of displacement analysis for this chain will study both the forward and the inverse kinematics. So, the chain is shown here. So, here you have this angle, which we will call theta 2, and this displacement S of the slider. So, we are going to look at the forward and inverse kinematics problem, assuming one to be input, the other to be the output. So, the forward kinematic problem. So, what are we given? What is the problem statement? We are given the input. Say input is the angle theta 2, and what is the output? Output is the displacement of the slider from a certain datum position. The datum position is taken here. From there we are measuring the displacement of the slider. Now, let us look at this chain. I will fix up a coordinate system. So, this is our xy coordinate system. So, in this coordinate system, the coordinates of point P, as you can see here, which is this hinge, is given by L2. L2 is the length of this link. So, the coordinates of point P is L2 cosine of theta 2. So, theta 2 is this angle. So, L2 cosine theta 2, which is the x coordinate of point P, and L2 sine theta 2, which is the y coordinate of point P. Now, coordinates of point Q, which is this hinge on the slider. So, that is, in this coordinate system, it is S in the x direction. So, this is x of Q, and E is the y coordinate of point Q. Therefore, the length L3, which is this coupling link, can be expressed as L3 square is equal to, here I have written like this, x q minus x p whole square plus y q minus y p whole square. So, that is the length of link 3. So, here I have the expression. So, let us open up these squares and see what we have. So, we have L3 square is equal to S square plus L2 square cos square theta 2, and from the second bracket we will have L2 square sin square theta 2. So, we will have L2 square. So, L2 square cos square theta 2 plus L2 square sin square theta 2 is L2 square. Then we have this cross terms minus 2s L2 cosine of theta 2. So, I am writing as c theta 2 in place of cosine theta 2. Then I have E square and I have twice E L2 sin theta 2. So, sin theta 2 I am writing as S theta 2. So, if I rearrange, remember that we are given theta 2 and we want to find out S, that is a forward kinematics problem. So, we have to get an equation for S. So, I can write it like this: S square, it is this term, then the term in S which is here. So, that is plus minus 2 L2 cos theta 2 into S, and then the rest of the terms plus L2 square plus E square minus L3 square minus 2 E L2 sin theta 2, and that must be equal to 0. So, therefore, I can write this as S square plus A times S plus B equal to 0, where you know that A is this term and B is this bracketed term. So, let us formally see this. So, this is what I have written out for you. So, we get this quadratic equation S square plus A s plus B equal to 0, where we have these definitions of A and B as we derived it just now. Now, we have to solve for S. Remember that we are solving the problem of forward kinematics in which theta 2 is given. So, we completely know A and B, therefore, I can solve for S from here. Once I solve for S, I can now find out the tangent of this angle theta 3. So, what is theta 3? So, if I take this x axis once again, the horizontal axis. So, theta 3 is the angle made by the link L3 or PQ. So, the angle of the link PQ with the horizontal, which is the x axis, is the angle theta 3, and tangent of theta 3. So, T theta 3 is YQ minus YP divided by XQ minus x p. So, if you just substitute these expressions of y q, y p, x q, x p from here, then you will get this expression of tangent of theta 3. So, once I have found S, I will substitute in this expression and I can calculate theta 3. So, let us collate these things what we have. So, we have this quadratic equation which we need to solve, where A and B are completely known in terms of angle theta 2 which is given to us. Now, you know the roots of a quadratic equation. So, these are the two roots. So, you have two solutions corresponding to this plus or minus, and once I have these two solutions, I will get two solutions for theta 3. Now, how to solve this? You need to consider the inverse of this tangent, and to calculate the angle correctly in the proper quadrant, you need to use the function a tan 2, which is there in all standard softwares and numerical algorithms or programs that you use for computation. So, here let me show you what this inverse tangent or arc tangent 2 does. So, it will take y and x and it will calculate this angle theta. So, if the situation is like this, so, I have drawn two situations in which both x and y are positive, and the other situation where x is negative and y is positive. So, by looking at the sign of y and x, this function is going to give you the right quadrant. Let us understand the solution now graphically. So, here I have drawn the mechanism once again. So, this angle is theta 2 which is specified. So, theta 2 is specified. What we have to find out is S. So, if theta 2 is specified and the link lengths are known, so this point is fixed. So, this was the hinge point P. This is fixed. What is not known is the location of the hinge Q. Now, this link L 3 can rotate about P, which is known. This line, this horizontal line, is the line of action of the slider, line of motion of the slider. So, this is the line of motion of the slider. So, slider can exist or move on this line. So, if you want to assemble the mechanism with at this hinge Q with this link PQ and the slider, then it is the intersection of this circle. So, intersection of this circle with this line of motion. So, as you can see, there are two intersections, one is what I have shown, the other is here. So, therefore, I can assemble the mechanism either in this black configuration or in this blue configuration. So, I have two configurations, two possible solutions. These are given by this plus and minus. Now, you can very easily identify which solution is which. So, L2 cos theta 2, remember, is the x coordinate of point P. So, x coordinate of point P, if you add something to it, then it is this solution. So, with the plus sign you get the black configuration, with the minus sign, so with the positive sign you get the black configuration, if you take the negative sign you will get the blue configuration. And then you can see that the angle theta 3 will correspondingly be different. So, this is theta 3 for the black configuration and this is theta 3 for the blue configuration. So, the correct quadrant will be obtained when you use A tan 2 function. Now, let us look at the inverse kinematic problem for the 3R1P chain. So, here we are given the slider position S, that means the output is specified, output S is specified. What do we have to find out? We have to find out this angle, the input angle. So, this is the inverse kinematics problem. Once again we look at these coordinates. Let me draw the coordinate system. So, this is the x, this is the y, and this is the angle theta 2, which now we have to find out given S. We have to find out theta 2. So, output is given, we have to find out what input angle will result in that output. So, once again we start with the same procedure. We look at the coordinates of point P. So, this is the x coordinate of point P, this is the y coordinate of point P, L2 cosine theta 2 and L2 sin theta 2. Right now theta 2 is not known. Then coordinates of point Q, this is the coordinate x coordinate of point Q and E is the y coordinate of point Q. Here S is known. So, length L3 can be expressed like this. So, therefore, if I open this, let me open this out. So, S square plus L2 square plus E square minus 2 S L2 cosine theta 2 minus 2 E L2 sin theta 2. So, these are the terms we obtain. Now, once again we know S, we are given S, we have to calculate theta 2. So, I can rearrange this in this form. So, I will divide by 2L2 and write it like this: E sin theta 2 plus S cosine theta 2 is equal to S square plus L2 square plus E square minus L3 square. So, therefore, this has this form: A sin theta 2 plus B cosine theta 2 is equal to C, where we can easily see that A, B and C, they have S and S is specified. What is not known is theta 2. So, we have to solve this equation to determine theta 2. So, this is what we are going to do. So, let me formally write this up. So, I have A sin theta 2 plus B cosine theta 2 is equals to C, and the definitions of A, B and C are given here. So, in the previous slide I missed this term. So, please include that. Now, once I have theta 2, I can solve for theta 3. The same procedure, tangent of theta 3 is equal to y q minus y p divided by x q minus x p. And if you substitute these expressions of y q, y p, x q, x p, then you will come to this expression. So, given S, we are going to solve this equation for theta 2. Once we have theta 2, we will substitute in here and solve for theta 3. So, the solution of A sin theta 2 plus B cosine theta 2 equal to C. Now, when you try to solve this equation on a computer, you need to get the all the solutions and the proper quadrants. So, in order to do that, we make this substitution as x equal to tan theta 2 by 2 and express sin theta 2 and cosine theta 2 like this, which you can easily check if you substitute this tangent theta 2 in here. So, you get 2 tangent theta 2 by 2 by 1 plus tangent square theta 2 by 2, and in the denominator you will get cosine square theta 2 by 2 plus sine square theta 2 by 2, which is 1 divided by cosine square theta 2 by 2, which comes to the numerator and gives us sine theta 2 by 2 to cosine theta 2 by 2, and which is sine theta 2. Similarly, you can check for the cosine theta 2 expression. Now, you substitute the sine theta 2 and cosine theta 2 in terms of x in this equation and get to this equation, which is a quadratic equation in x. So, you have to solve for the roots of this quadratic equation, which will give us x, and x is tan theta 2 by 2, x is tan theta 2 by 2. So, once we have the solution for x, we have the solution for tan theta 2 by 2. So, these are the solutions for x, which is same as tan theta 2 by 2 in terms of the capital A, B and C. So, I have written this solution out once again, and you have to take tangent inverse. Now, because of these two signs plus and minus, there are two solutions which I name as theta 2 1 and theta 2 2. Once I have these two solutions, theta 2 1 and theta 2 2, I can go over to this tan theta 3 expression, substitute 1 by 1. So, theta 2 1 and theta 2 2 and get the expression for theta 3. I can solve for theta 3. Once again, we will use this a tan 2 function when we are solving it on the computer. On the calculator, you can find out the values appropriately in the quadrant. When you do by hand using a calculator, you use tan inverse function and you will get one solution for the angle, and as you know that there will be another solution at a difference of pi. So, here is the graphical interpretation of our solution. What we were given, we were given S was specified. If S is specified, this gets locked. So, this hinge is known, this hinge was named as Q. What is not known is this hinge P. Now, this link L3 can be made to rotate on this circle. So, P on link 3 can move on this circle, whereas P on link 2 can move on this circle. So, there are two intersections, one is this, the other is this. So, you have two configurations, two possible assembly modes. One is this black one which I have shown, the other is this blue configuration. Which I have drawn. Correspondingly, you will get the angle theta 3. So, here this is theta 3. In this case, it is this angle that is theta 3. This whole angle. You can consider this angle as theta 3, which is the coupler angle. So, here we have this angle, here we have this angle. So, there are two solutions. Now, whether it can go from one solution to the other, that depends on whether the chain is Grashof or not. So, finally, let us summarize. We considered the displacement analysis and we took the example of the 3R1P chain of type 1, and we have looked at the inverse and forward kinematics of the chain and looked at the graphical interpretation of the solutions as well. With that, I will close this lecture.